What's up, mathematicians? Justin here, and in this video we'll be looking at sine, cosine, and tangent. So in the previous lesson we highlighted the assumption that two triangles can be similar. In other words, it's possible to have two triangles with all corresponding angles equal but different sizes, one being larger than the other. Now we're going to take that a step further and say that if two right triangles have one other angle that's equal in both, they're similar. Where this leads us is we're going to end up assuming that all right triangles must have the same angle sum. And it's these assumptions that enable us to use sine, cosine, and tangent for measurement. Okay, let's talk for a minute about the assumptions that I just mentioned. Specifically, this assumption that all right triangles have the same angle sum. And, I'll go ahead and give it away. It's 180 degrees. It's possible you're already yelling that at the screen right now. I know what it is. All triangles have an angle sum of 180 degrees. Okay, yeah, we'll get there. There's a lot more to unpack here than you may realize, or maybe you do realize. But let's talk about why we need that assumption to do the trigonometry that we want to do, to work with sine, cosine, and tangent. So let's draw two right triangles that are similar. So I'm just going to do one here. That's length 3 here, and length, 4 here. Take advantage of this dot grid paper to draw this easily. So here's a right triangle. And in order to easily draw another right triangle that has that's similar, I'm just going to double all of these. So instead of 3, I'll do, here, I'll do 6, and then 2, 4, 6, 8 here. So let's go ahead and draw in this larger triangle. Okay, so these are both right triangles. So these angles are equal. Now let's go ahead and take a step further and say these angles are equal, and the variable that we're going to be using for an unspecified angle is theta. So let's go ahead and say that both of these right triangles have an angle here that's equal. Now in order for our trigonometry that we're going to learn to work, we need to have these angles here be the same as well. Well, let's go ahead and say that this angle up here is x and this angle up here is y. Well, if we can say that 90 degrees plus theta plus x is equal to 180 degrees, which is what we're claiming is the angle sum of all right triangles, 180 degrees, which is also equal to, in this triangle, 90 plus theta plus, in this case, y. Well, since this is equal to 180 and this is equal to 180, then this must equal this. Well, this part here and this part here are the same, which means that what I'm left with is x and this y must be equal. So if we make this assumption that all right triangles have the same angle sum, we get this payoff, which is going to be really useful for the trigonometry we're going to do, which is that if you have two right triangles in which another angle theta, we'll call it, is equal in both, then those two triangles are similar. And they're going to have that rule of proportionality that we talked about in the last video. Let's get back to these ideas of sine, cosine, and tangent. What are these things? What are sine, cosine, and tangent? Well, you can see here on the screen a whole bunch of numbers, and you might see at the top there sine, cosine, and tangent. So maybe they're just numbers. Well, it turns out that, at least for now, we're going to be looking at sine, cosine, and tangent as ratios. Sine, cosine, and tangent, for our purposes, are ratios. They are relationships between two numbers. Now, in a future math class, you'll probably look at them more as functions. But for now, we're going to stick to them as being ratios. And they depend on this assumption that all right triangles have the same angle sum for us to be able to work with them as ratios, as we will need to do. Okay, now that we know what they are, they're ratios, let's go ahead and define them. We're going to start by drawing a right triangle. So for now, sine, cosine, and tangent are always going to be used in the context of right triangles. Later on, you'll learn to use sine, cosine, and tangent in other contexts, but for now, they are really just things that we use when we're working with right triangles. So we're going to draw a right triangle here. And here's our right angle. And then in this right triangle, we have some angle theta. Now, with reference to this angle theta, we have three sides. First, we have the long side, the longest side of the triangle, and that side is always across from the right angle. We call that the hypotenuse. I'll abbreviate it as HYP. Then for the two remaining sides, which are called legs, we have one that is across from the angle theta. We call that the opposite, and we have one that's next to or touching the angle theta, and we call that the adjacent because it's next to or touching the angle. So three sides: hypotenuse, opposite, and adjacent. So the definitions of these ratios are as follows. For the sine of the angle theta, the ratio is the length of the opposite side to the hypotenuse. For cosine of theta, the cosine of theta is equal to the ratio of the length of the adjacent side to the hypotenuse. And finally, tangent of theta is equal to the ratio of the length of the opposite side to the adjacent side. Now, one mnemonic that many students find helpful for remembering these ratios is the mnemonic SOHCAHTOA. You may have heard this mnemonic before, and so let's go ahead and look at how this mnemonic can help us remember these definitions. So SOHCAHTOA. So the idea here is that we have the sine equaling the opposite over the hypotenuse. S is O over H. Cosine is equal to the adjacent over the hypotenuse, adjacent A over H. And finally, tangent is equal to opposite over adjacent. So that's a mnemonic that may help you remember these definitions. Okay, so who cares? We have some ratios. Why does this matter? Well, it turns out defining these ratios is going to give us a tool that's very useful for being able to measure many, many things. Buildings and bridges and play sets, what have you. Architects and carpenters and people like this use trigonometry, use sine, cosine, and tangent all the time. Even if they don't realize they're using it, the computer programs that they're using to draw things are doing trigonometry under the surface, even if they're not doing the sine, cosine, and tangent calculations themselves. Okay, so what are these ratios? Well, I have here a table, and we can see here the angle, sine, cosine, and tangent. Okay, so for some angle, let's say 30 degrees, the ratio of the length of the opposite side to the length of the hypotenuse is 0.5. That means that in any right triangle, the length of the opposite, for any right triangle where one of the angles is 30 degrees, the ratio of the side opposite the 30-degree angle to the hypotenuse is always 1/2. The opposite side is always half the length of the hypotenuse. It doesn't matter if the triangle is as small as like a penny or as large as, you know, the galaxy or the solar system. I mean, we could be talking about huge right triangles or super tiny right triangles. That ratio always stays the same. That comes from that proportionality fact that we talked about in the last video. The fact that if two triangles are similar, the proportions will be the same. Doesn't matter how big or how small. So we have all these numbers, and you might wonder, like, where do these numbers come from? How do we know that this ratio is, you know, 1/2? Well, it turns out the answer to that question is simpler than you might think, and it involves measuring. Let's look at how we might find the sine and cosine of a 20-degree angle. So we can see those things right here. We know the answer we're looking for, but let's go ahead and see how we can use measurement to get those ratios. So first thing I need to do is I need to draw a triangle with a 20-degree angle. And so for that, I'm going to need my protractor. So let's go ahead and make it, you know, fairly large here. I'm going to move this paper up, and I'm going to put it, let's see, I'll bring it down here, and I'll just draw a nice long line across my paper here. Okay, so there's my line, and I'm going to now make a 20-degree angle. And I'll go on my protractor. Here it is. Now you might see a 160 there. That would be if I was moving from the other direction. From here, 0, that should be a 10, and then this is 20. Okay, so now let's go ahead and extend this line out. Now I'm going to go ahead and draw two triangles, one smaller and one bigger, so we can see that these ratios actually do stay the same. And let's see, I'll do the smaller one here. I'm using the dots on my dot grid paper to make these perpendiculars. And then I'll draw the bigger one over here. Now it's time to do some measuring. So let's get out our ruler. I'm going to need to measure these lengths. So let's see. First of all, this length along the bottom of the smaller triangle looks like 7.5. This is all going to be in centimeters. And the length along the bottom of the big triangle turns out to be 17.5. So I'll put it down here. 17.5 is this length here. Oops, I shouldn't have ended it there. This length right here up to there. Okay, now let's find the lengths of these heights. So let's see, that looks like, let's go with let's try to make this as exact as possible. I'm going to go with 2.7. So 2.7 centimeters. And now let's measure the height of this triangle here, the length of that side. And that comes out to 6.3 centimeters. 6.3. And now we need to measure the hypotenuse for both of these triangles. So first off, okay, so it's right about there. So this is going to be 7.9. I'm going to go with 7.9. So that's the length of the hypotenuse of the smaller triangle. right here. And now let's find the length of the hypotenuse of the bigger triangle. All right, so now I come out to here and I've got, it's kind of between 18.5 and 18.6. I think 18.5 is closer. So I'm going to say 18.5. So the large triangle has a hypotenuse of 18.5. Okay, so let's start with sine. The sine of 20 degrees, I should have put that in here. This angle is 20 degrees. This, of course, is my right angle. And since these angles have to equal 100, or have to add up to 180 degrees rather, we know that this top one is going to end up being 70 degrees. But we don't need that for our calculations right now. So the sine of 20 degrees is equal to the opposite length, and we'll do the smaller one first, 2.7, divided by the hypotenuse, 7.9. Let's go ahead and plug that in our calculator to get a decimal approximation. 2.7 divided by 7.9. And I get 0.34. I'm going to round to the nearest hundredth. So when I round to the nearest hundredth, I get 0.34. Okay, let's do the same ratio, or let's find the sine of 20 degrees using the larger triangle. So we should end up with the same ratio. Now it's possible with measurement error and such, it'll be slightly different, but it should be very close. So with a larger triangle, we have the opposite side length 6.3. So 6.3, and the hypotenuse 18.5. So 18.5. Let's go ahead and do that division. So let's see, 6.3 divided by 18.5. Once again, if we round that to the nearest hundredth, that's going to give us 0.34. So turns out that within the nearest hundredth, my measurements seem precise enough in the sense that I got the same thing. Now that doesn't mean they're perfectly accurate. We'll check the table later. Let's go ahead and do cosine as well. So the cosine of 20 degrees is equal to the adjacent. So we'll do the smaller triangle first. The adjacent is here. 7.5 divided by the hypotenuse, 7.9. And let's go ahead and calculate that. 7.5 divided by 7.9. I get 0.949. So if I round in the nearest hundredth, it's 0.95. 0.95. And now let's do it with a larger triangle. So the cosine of 20 degrees is equal to 17.5 divided by 18.5. Let's plug that in the calculator. 17.5 divided by 18.5. Once again, if I round to the nearest hundredth, I'm going to get 0.95. Okay, so 0.95. All right, let's go ahead and check our table, see how close we are. So 20 degrees, we see here that the sine of 20 degrees should be 0.34 if we round to the nearest hundredth. And what do we get? 0.34. We're right on track. Now the cosine, if we round to the nearest hundredth, should be 0.94. We got 0.95. So we're off by 1/100th, which is a measuring error. The tools I'm using are not perfect. But the point here is that in order to find these ratios, all you have to do is make a right triangle with the specified angle measurement. measure the sides, and you can calculate the ratio. And it doesn't matter how big or how small the right triangle is, because we're assuming that all right triangles have the same angle sum, and therefore being any right triangle having a 20-degree angle is similar to any other right triangle having a 20-degree angle, which means that that proportionality principle that we talked about in the last video holds, and we can use that ratio for any triangle at all that we come across with that angle measure. This ends up being really powerful. Maybe you can't see how powerful yet, but future videos we'll get into it. Now, I know we didn't do the tangent here. I kind of ran out of space, and I think we've gone on long enough. So I would encourage you to use the measurements here, calculate the tangent, and see how close it is to this number right here, 0.36 if you round to the hundredths place. Okay, so that is a quick introduction to sine, cosine, and tangent, the three trig ratios, which we'll be using in the next few lessons. I hope that was helpful to you, and in future videos we'll be looking at applying these ratios, sine, cosine, and tangent, to solve some problems. Hope to see you then.